is from the PowerPoint slide. I didn't have it written in the note pack, so it was a visual I needed to pull up, so thanks for your patience. What we have is generating two lists, and these could be lists right into your calculator. In list 1, we have time. As time goes by, we're measuring the disappearance of the reactant. At time 0, it's 1 molar. 200 seconds go by, it's down to 0.88. 400 seconds go by, we're down to 0.78, and so forth. If we graph this data, it looks like this kind of slope. And again, we could do this on our calculator list and generate a graph, and at this point, we'll just take a look at one that's been generated. I want to find two convenient points to find how varying the concentration affects the overall rate. The first one I noticed is an intersection here at about 0.8, time is 400. Cut that concentration in half to 0.4, and again, at about 0.4, I'm down about here. I have a time of 1600 seconds. So cutting the concentration in half affected the rate from 4 to 16. This information is what's being used then to generate the next question from our notepad page. So when I find a rate, molarity per second, let's suppose at this instant in time, 0.8 per second, time interval that went by is 400 seconds, we can come up with a rate. We did the same at a different concentration. We set an average rate as time goes by, would set up molarity per second for the rate at 0.4 molar. We solved for 0.4 molar and 0.8 molar instantaneous rates. We solved for the tangent of the line, molarity per second. How did changing the concentration affect the rate of our reaction? And so this is just done graphically for us, and I didn't put it into the notes. Alrighty. But these are the values that are interesting to us. The rate at 0.4 molar is 2.963 times 10 to the negative fourth molarity per second. The rate at 0.8 molar is 5.926 times 10 to the negative fourth molarity per second. Now, they have negative signs because it is a negative slope, but I'm stressing that rates are always positive. It makes no sense to have a negative velocity. So I left the negative signs off. They're there by convention to remind us that reactants are disappearing. They're not telling us that it's a negative rate. What we're being asked then is, how does the concentration affect the rate of our reaction? So we generate these lists in a data table. List 1 represents time going by. List 2 represents the concentration. We graph that information, concentration versus time, and we solve just convenient points. 0.8 and 0.4 were selected because they're half of one another. We solve to find the instantaneous rate by finding the tangent of the line, and that's a calculus move I'll show you in a bit. We did the same thing at 0.4 concentration. We found the instantaneous slope. And all we're doing there is saying at that instant in time, we have a rate of molarity per second. We stand back and we say, how did the rate become affected by changing the concentration? And in my head, if I were trying to compare these two numbers, this is what it would look like to me. Times 10 to the negative fourth is the same for both, so I'll just disregard. 2.963 is pretty close to saying 3. 5.92 is pretty darn close to saying 6. If I doubled the concentration, the rate also doubled. 0.4 doubled is 0.8. 3 doubled is 6. When I double the concentration, the rate then doubled. Since the rate at twice the concentration is twice as fast as the rate, well, the rate law must be first order with respect to our reactant. It had nothing to do with the stoichiometry. The only way to determine this is to run the experiment. Now let me go back to the note pack. Again, I needed to pull those slides to show what we were comparing. So if you have your PowerPoint up in a different window, you can see those lists and how we go through and actually graph those. But the conclusion was this. Through the process of graphing, we said at 0.8 molar, the rate was determined through an instantaneous rate method to be 5.926 times 10 to the negative fourth. At 0.4 molar, we found the rate to be 2.963 times 10 to the negative fourth, and rates are given units of molarity per second. My logic was to disregard 10 to the negative 4. It's the same for both numbers. If I doubled the concentration, the rate did the same thing. Think of it this way. If I doubled the concentration, what power do I raise that number to double the rate? 2 raised to the first power is 2. This must be a first order reaction with respect to N2O5. Rate is equal to K times the concentration of that reactant, N2O5, raised to the first power. We say that it's first order with respect to N2O5. On a side note, the other reaction that we would study, we said we'd study zero order, first order, or second order. Suppose we doubled the concentration and the rate quadrupled. Doubling the concentration made the reaction go 4 times as fast. What order with respect to the reactant? Well, 2 squared gives us 4. If we see that pattern, it would be second order with respect to the reactant. And once in a while, we'll have a zero order, and that just means there's no effect. If I double the concentration, triple the concentration, there is no effect on the rate, and it just drops out of the reaction altogether. And typically that will happen for catalysts since they're not reactants or products. So a zero order, no matter what we do to that concentration, I see the reaction rate not doing anything. It just stays the same rate overall as if I hadn't changed it. We call that a zero order. The only way to run this experiment, varying the concentrations, initial rate method, and recording the rate. Alrighty. So again, we say that this reaction is said to be first order with respect to N2O5. It was a direct power relationship. So in general terms, if we have back to our general chemistry formula, A plus B going to C plus D, the rate law comes from the reaction